Good morning and welcome to the very first topic in Honors Algebra 2. This is very exciting, although this topic is not so exciting because it doesn't really have any math in it. It's mostly just vocab, but vocab is the thing that people tend to forget more than anything else. So none of the stuff in here is hard, and you've probably seen it before, but it wouldn't surprise me if you don't remember seeing it before. Today we're going to look at sets of numbers, and we're also going to be looking at different types of notation. We have learning target for today. Learning target is I can classify and order real numbers. Some vocab before we get started. A set is a collection of items called elements. Usually in our math class, these items are numbers, but they do not have to be. We can have a set of dishes. That would just be all the dishes we have. Each dish would be an element. In math, we tend to use numbers, so we could have the set of numbers on a six-sided dice. 1, 2, 3, 4, 5, 6. Each of those is called an element. We can have a subset. A subset is just a collection inside of that set, a smaller part of that. So we could have the even numbers on the dice. 2, 4, 6. That's a subset of the larger set because all of those numbers are included in the bigger set. And we can also have something called the empty set. And that's just a set containing absolutely nothing. So it happens more often than we'd think, but it means that it just can't happen. It happens so often it actually has its own symbol. It looks like a 0 with a line through it. It's actually the Norwegian Scandinavian letter that I cannot remember the name for it. I just remember that I could never actually pronounce the name for it. But it's like it's that O with the line through it, kind of like in fjord. On a note there, if you're in a habit of drawing zeros with a line through it, making it look like this, that is not a good thing because they mean two completely different things. And so that gets us to some sets of numbers. We have a bunch of sets of numbers. We're going to start out with the simplest, oldest set of numbers that there is, and that's called the natural numbers, also called the counting numbers. And that just starts, it's how we count. 1, 2, 3, 4, 5, 6, 7, etc. Notice what this does not have in it. It does not have a lot of things in it. It's just things that we count. And this set of numbers has been around for thousands of years. It doesn't necessarily look like this, but people have been using these numbers forever. And each of these sets of numbers has a symbol. Natural numbers, we use an uppercase N. And we use a specific font called Blackboard Bold because the chalk on my blackboard does not have a bold button on it. So it has a double stroke down it. The font doesn't necessarily make a difference. If you use a capital N, people know what you're talking about. The second set of numbers are called the whole numbers, and this set of numbers has been around for a few thousand years. There was an amazing invention that differentiated the whole numbers from the natural numbers, and that really changed the way math worked, and it changed just amazing stuff in the world. And that invention was the number 0. For thousands of years, there was no need for a number 0 because if you're counting, you don't start off with 0. If I was going to list what I had, I don't say that I have 1 dog, 3 cats, 1 fish, 0 alpacas, 0 lions, 0 birds, 0. I mean, there's a whole lot of things that I have nothing of. And so you never listed them. But in inventories and stuff, having a symbol for 0 was very important and useful. So the whole numbers are just natural numbers plus it added 0. Notice the natural numbers is a subset of the whole numbers. And the whole numbers have a symbol too. Natural numbers has N, so whole numbers obviously has the W of that same font. Next up, we're going to add in the negatives, and that gives us what are called the integers. So the integers are defined as the whole numbers and their opposites, the opposites being the negative numbers. So notice we still don't have any kind of decimals or anything, but we have all the positives, all the negatives of the whole numbers. And the integers has a symbol as well, and that symbol is obviously going to be z. It's not actually obviously z. It is z, but that's not hugely obvious. I've heard a couple different stories behind why it's z. One is z is the first letter of one of the German words for number. A couple other things, but nothing that's super official sounding. We don't use I because we use I somewhere else. The next setup, we get the rational numbers, and this is where we start adding in fractions. So a rational number is defined as any number that can be written as a fraction, which is also decimals that end or repeat, because any decimal that ends or repeats, we can write as a fraction. And so the rational numbers, obviously, gets the symbol Q. Again, not obvious. We're saving R for later. Q actually stands for quotient. A quotient is just something divided by something else. It's the answer to a division problem, which is the same as a ratio. In fact, the division sign, that little dot with a line and another dot, is just a symbol for a fraction. We have something over something. And so notice, again, the natural numbers are a subset of the whole numbers, which are both subsets of the integers, which are both subsets of the rational numbers, because we can write these as fractions. 2 over 1, that's a fraction. The next set of numbers is not part of the rational number set. It's separate from the rational numbers, and it's called the irrational numbers. And irrational simply means not rational. So it's any number that cannot be written as a fraction or a decimal that ends or repeats, which means it's any decimal that neither ends nor repeats. There's a couple fairly common famous ones. The one that you're probably thinking of right now is, oh, it's not that. Irrational numbers don't have a symbol. So if you can abbreviate it IRR, pretty much anyone who should be looking at anything should know what you're talking about. Anyway, back to the one, the irrational number you're thinking about. It's probably pi. It's irrational. It never ends or repeats. Everybody knows that, but a lot of people don't actually believe that. It's like, how could that even happen? Well, we have a couple more really common irrational numbers. One of them's e. Yes, the number e. We will be learning about that later on this year. Which is my second favorite irrational number. Pi is not my first. My first is actually phi. That's the golden ratio, which unfortunately we don't really get to learn about all that much this year, but it's a fun irrational number. So how can a number neither end nor repeat? Well, let's take a look at another number. 0.10, 110, 1110, 11110. Are those repeating? No. Is it a pattern? Yes. But that pattern's not repeating. We're never repeating the same set of numbers over and over and over again. Could I keep doing this forever? Sure, I could. And so this is an irrational number. If you had to find an irrational number in between, say, 1 and 2, 1.10, 110, 1110, etc., that would be an irrational number. You can put this in between anywhere. Between 2.3 and 2.4, 2.3101101. You can do it anywhere. And it doesn't even have to be those numbers. You can use any numbers you want. But there's a pattern there that will continue and won't stop. Another good one, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc., etc. I can keep adding numbers onto the end of that. It's not going to stop. It's not going to start repeating. So that would be another irrational number. And then if we take all the rational numbers and all the irrational numbers, which there is no overlap, but if we combine those two sets, we get the set that's called the real numbers. And that's any number that you're going to possibly be able to think of at the moment. Are we going to learn about numbers that aren't real this year? Yes, we are. What's not a real number? Well, obviously it's imaginary. And no, I'm not making that up. It's a complex topic, but we'll get there. And the real numbers have a symbol. That's where we use R. So we don't use it for the rationals. The real numbers is what we use more often than anything else. These are just more special cases where we'd use like any of the subsets. So those are sets of numbers. Now let's look at some types of notation, because we are going to be using some notation as well. We have a few types. The first type is called roster notation. And for roster notation, you use the squiggly brackets and you just list all the possible combinations. For example, if we roll a dice, what could we possibly get? We could get 1, 2, 3, 4, 5, or 6. So roster notation is really easy, really simple, but it must be a discrete set. You cannot use it for a continuous set. So you can't use it if you mean for all the real numbers or all the rational or irrational numbers. Because this, as we list out, it does not include 2.1. It doesn't include it. It includes 1, 2, 3, 4, 5, and 6. We can use other things. We could do the empty set. Remember, the empty set is a set with nothing in it. So how could we write a set with nothing in it using roster notation? Well, we use the squiggly brackets, and we put nothing in it. So that's another symbol for the empty set, by the way. We can do infinite sets, like we could do the natural numbers. We just have to develop a pattern. So the natural numbers is 1, 2, 3, 4, etc. But again, it does not mean 1.1, 1.5, 1.37, none of that. It's just 1, 2, 3, 4, and then the pattern will continue. If we want a continuous set for the real numbers, we can use one of the next two types of notation. And these two types are actually very, very similar. The first type is interval notation. And with interval notation, we use parentheses or the square brackets to put it around the endpoints of the numbers that we want. For example, 3, 5. I have a parenthesis. A parenthesis is singular for parentheses. You don't get to use it very often, so use it while you can. And then I have a square bracket over here. Now those could be reversed. They mean different things. We'll talk about the meaning in just a second. But what this set of numbers, what this interval is, we could write using inequality notation, which is the other type that's similar. And this is going to be 3 is less than x is less than or equal to 5. These two things mean the same thing. One of the biggest differences between the two is that in inequality notation, we have to pick a variable. I picked x. It doesn't have to be x. I just picked x. Other than that, the symbols. We have the less than, greater than. Well, that's going to be the curved parentheses. Curved parentheses are just for less than or greater than. If we want or equal to's, we use the square parentheses. So notice the 3 has curved one, it's less than. The 5 has a square one, and it's greater than or x is less than or equal to 5. So it doesn't have to be just those two. They could both be the same. 0, 1 is the same as 0 is less than x is less than 1. Negative 2, 9. Notice the square brackets over here. It's negative 2 is less than or equal to x is less than 9. Or they could be both less than or equal to. 0.5, 0.6 with both square brackets means that they're both or equal to. So these two are really easy to switch between. Sometimes one makes more sense than the other to use, but they are really interchangeable. And the last type of notation that we have to look at is called set builder notation. We won't use this so much this year, but it is the basis of what we would do in upper mathematics. And really, it's not much different than inequality notation. It just allows us to specify more things. In general, we're going to start out with the curly brackets, and then we have to define our variables. I've defined one variable. We could define more than one variable here if we wanted to. But x, this little line, means such that. And we have 3 is less than, or x is less than or equal to 5. I just use the same interval as this one. And then we can actually define the subset that it's in. Here, normally, x is an element of the real numbers. That's what this little e thing means. Is an element of. But if we leave off this part, it's automatically the real numbers. But we could use the natural numbers. We could use the irrational numbers. Hey, I want all the irrational numbers in between 3 and 5. We could put irrational there. We could use the rational. We can specify what set we want. Whereas these guys are for the real numbers only. So this allows us a little bit of extra control over what we're doing. But basically this is going to be the same as the inequality notation. Most of the time, you're not going to have to make anything in set builder notation here, but there may be a couple times when you'll have to read set builder notation. Look at the interval. That's the important part. And so that's section 1. Again, notice there's no math here. It's all vocab. We'll get to math in a couple sections. Just hang in there and enjoy the vocab while it's here.